why do we know that 7 is a generator for this clock group Z12? What does it mean to be a generator again? Ah, right. So you're skipping straight to the answer. Yes, you're absolutely right. So the ultimate answer at the end of the day is going to be, and this is important in this chapter, because 7 is relatively prime to 12. I'm going to write that as this. GCD of 7 and 12 is equal to 1. Right? And so there's a number theory reason for why or how we're going to be able to tell that something is a generator of the additive group mod n, right? Because of relative primeness. But how could I see that 7 generates this group? Well, 7 to the power 1 is just 7. 7 to the power 2 in the additive group mod 12, remember, is the same thing as 7 plus 7 mod 12. And what is 7 plus 7 mod 12? 2. Then when I add 7 again, I'm going to get over to 9. When I add 7 again, 9 plus 7 is 16, which is 4. I add 7 again, I'm going to get to 11. I add 7 again, 7 hours later, I get to 6. 7 hours after 6 o'clock is 1 o'clock. 7 hours after 1 o'clock is 8 o'clock. 7 hours after 8 o'clock is 3 o'clock. 7 hours after 3 o'clock is 10 o'clock. 7 hours after 10 o'clock is 5 o'clock. 7 hours after 5 o'clock is 12 o'clock. And now we've gotten them all. Right? So 7 is an example of a generator for the finite group Z12, but now that we know that there exists a generator, we can say that we know for sure that this group is cyclic. So 7's an example of a generator. Is it the only generator for Z12? Leading question. You're shaking your heads. What's another example of a generator for Z12? Grace? 5's another example. Whoops. For the same reason as 7. In fact, 5 and 7 have a special relationship to one another. What is it? They're inverses. Yeah, they're inverses to one another in this group. And so if 7 is a generator, then of course 5 is also going to be a generator because, and this is a theorem you can take to the bank, that if A is a generator for a cyclic group, then so is A inverse. So is A inverse. And that's a theorem, which might be one of the things that we try to prove over the next couple of days. Right? So as soon as I find a generator, I also get another generator just by just taking its inverse. So 7 and 5 are both generators. What are some more examples? Casey?
1 and 11.
1 and its inverse, 11. Exactly. 1 and 11 are inverses to one another, and they both happen to be generators. Why is 1 a generator? Why, in some sense, should 1 be the most obvious generator for this group, Kenzie?
Because 1 plus 1 is 2.
Plus 1 is 3, plus 1 is... Exactly. This is just the ants marching kind of generator for this group, right? If I take 1 and I add it to itself, I get 2. I add another 1, I get 3. I add another 1, I get 4. So I'm not hopping around the clock haphazardly like when we were adding 7s, right? I'm just generating all of the residues from 0 to 11 just in their linear order when I add 1 repeatedly to itself, right? Are there any other generators for Z12 besides 1, 5, 7, and 11? Well, if we have a theorem, and we're going to have this theorem today, that an element, or let's say a number, n, generates Z mod k, so n generates zk, if and only if n and k are relatively prime, then are there other generators for Z12 on this clock? 0 can never have a common factor of 1 with anything. The greatest common factor of 2 and 12 is 2. 3 shares a factor of 3. 4 shares a factor of 4. 6 shares a factor of 6. 8 shares a factor of 2 and 4 with 12. 9 shares a factor of 3 with 12. 10 shares a factor of 2 with 12. And so every other number on this clock is not relatively prime to 12. Just 1, 5, 7, and 11. By the way, where else have we seen the set 1, 5, 7, and 11? should have given the exams back first, because this set was on the exam as one of the problems. Casey?
It's U12.
It's U12, which is what? So it was a group, right? And it used the same modular kind of arithmetic, but what's the operation in U12?
Multiplication.
Yeah, group under multiplication. So that is a serious connection. And the serious connection here is that it's exactly those elements that are relatively prime to 12, those numbers that are relatively prime to 12, that are also the numbers which are going to have multiplicative inverses mod 12. Right? And it's the inverses that would otherwise get in the way of these other things being part of a group under multiplication mod 12. I should say mod 12 here. So this is not an accident, right? The number of generators in Z mod K is the same thing as the number of elements in UK. And both of those things get a special name in number theory. So any of our number theory people remember the name for the number of elements that are here / the number of generators that are in Z12? This number in this case is 4. Your daily work gave you a chance to wrestle with this a little bit already. Yeah, well, in some cases, p minus 1, when p is a prime. So the number of invertible elements, invertible elements, mod 12, is the same thing as the number of generators of Z12 both of those things are a special quantity in number theory. Called the Euler function, or the Euler Phi function. So this is a little Greek letter phi. When I write this particular usage of phi, I'm usually going to use this little curly version that looks kind of like a weird cross between a y and a p. There might be other places where I use the letter phi and I write it in this sort of more standard way, but whenever I'm talking about the Euler Phi function, I'm going to try to use this curly version just so that we keep the two straight. And this is its definition. Its definition is that it's defined to be phi of k is the number of relatively prime residues to k. Relatively prime numbers that are relatively prime to k that are less than k. Right? So how many numbers less than 12 are relatively prime to 12? 1, 2, 3, 4. Same as the generators over here, 1, 2, 3, 4. And so, for example, phi of 12 is equal to 4. And daily work number 10 that I gave you to work on over the break, one of the things that you do on daily work 10 is wrestle with how to compute this number, phi of k, for various values of k. So what we should keep in mind for abstract algebra is what it tells us. Phi of k tells me two things. It tells me how many generators the additive group mod k has. It also tells me how many elements the multiplicative group mod k has. So it's a multi-tool. And if you take number theory, that function, the Euler Phi function, becomes like a staple of almost everything you do in the theory of the integers, because it has so much to do with divisibility. If this is the clock model for cyclic groups, then what's the number line model? What kind of cyclic groups could be modeled by a number line? Infinite cyclic groups, which are in a way a little bit less interesting than our finite cyclic groups for us. So let's think about this model for just a second. So as a number line would do, it goes infinitely far in both directions. Kind of draw arrows here to indicate that. But this is a group, and so since it's a group, it has to have an identity element somewhere. Let me put that identity element maybe right here in the middle. And if this is indeed a cyclic group, then what does it have to have? Besides an identity element, what else has to exist? A generator. That's what cyclic means. So that means there's got to be a generator in here. Where should I place my generator? thinking about the number line metaphor, I should probably place my generator right after it, because what if I didn't? What if I sort of skipped some spaces? What if I thought of this as being my generator over here? If this is A, then where should I put A squared, A plus A, just in this mental picture of a number line? If A is sort of like 3, then where would A plus A go? 6, and then 9, and then 12. And I'd be skipping over some of the integers on my number line. Right? So again, in my mental cartoon bubble for an infinite cyclic group, I want to put that generator right next to it so that I can kind of model the multiplication by A as, again, this operation of just kind of taking successive steps to the right. So there's A squared, there would be A to the third, A to the fourth, A to the fifth, and so on and so on. That accounts for the whole this side of the number line, but what exists on that side of the number line? What would be the first element to the left of the identity element?
A inverse.
A inverse, exactly. But wait a minute. What do the powers of A inverse then generate? If I take one more step to the left, what do I have? A to the minus 2, A to the minus 3, A to the minus 4, and so on and so on. Right. Casey?
So in this case,
So we saw in the finite cyclic groups example that a finite cyclic group can have a whole bunch of generators, right? Depending on the order of the group itself. Here the order of the group was 12, and the number of generators was phi of 12, which was 4, right? The Euler Phi function. So this cyclic group had 4 generators. This cyclic group at least has 2 generators, as Casey observes here. We know that if A is a generator, then the inverse of A will also be generator. Either one of these will generate the whole group. But can any other element of this group generate the whole cyclic group? Let's work on a quick proof of the negative. So, claim that there are no other elements may generate an infinite cyclic group. Infinite cyclic group. Besides, I should write this here, besides its generator and the inverse of that generator, no other elements may generate an infinite cyclic group. So let's think about why that is. What I want to do is pick an element which is neither A nor A inverse, nor the identity. Right? Try and pick something that's interesting. Let's suppose that I pick this element over here. Let's call it B. So let's let B be not equal to A or A inverse or the identity. By the way, why don't I want B to be the identity? What does the identity generate? Itself. It only generates itself. It has no power to do anything other than stay put. The identity is a homebody. So we don't want B to be the identity because we know what's going to happen in that case. So let's let B neither be A nor its inverse nor the identity. And I want to know, what does B get to generate? Can B generate the whole group? In particular, well, let's think about this number line model for a second. What does it look like B is in my picture? It looks like it's A to the 2, 3, 4, 5, 6. It looks like A to the power 6, right? And if B really were A to the power 6, what could it not generate? A to the power, well, it could generate A to the power minus 6, because it's inverse. It to the power minus 1 is going to give me A to the minus 6. It to the power 0 is going to give me the identity. It to the power 1 is going to give me B to the 6th. It to the power 2 is going to give me a B to the 12th out here somewhere. But that's missing a lot. In particular, what do we know it's going to miss? What can B not generate for sure? A to the power 7. And if it can't generate A to the power 7, it also can't generate A to the power 7 minus 6. What about A to the power 1? Right. So let's see if we can come up with that argument. So my burden of proof now, we will show that B cannot generate A. All right, so how do we know that B is not going to be able to generate A? We got to make this picture general. We've got to make it as general as we can. So if we don't know that B is A to the power 6, if this is a cyclic group, what do we know that B is for sure? A to the something, exactly. A to the power, I don't know, what do you want to call it, j? Where what is j? It's some integer, and what is it not? It's not -1, it's not 0, and it's not 1. Exactly. Because we assumed that b was neither a, nor a inverse, nor the identity. Right? So j is some integer, but it's not -1, 0, or 1. And so, argue by contradiction. Suppose b generates a. If b generated a, then what would that mean? This would mean that b to some power is equal to a for some integer. But on the other hand, we know that b is already itself a power of a, right? So a to the j is equal to b. So we'll put that a to the j. I'm not modeling very good proofwriting here. This is all one big giant cocktail napkin right now. But that's just going to have to be how it is. But what is a raised to the j raised to the k? How do I simplify that? Yeah, just multiply. Just use the general properties of exponents. A to the j times k is equal to a. And if I want to do something with this equation, I'm going to try to get all the a's onto one side. How can I get all the a's onto one side? Divide. And what does divide mean in abstract algebra? By the inverse. Exactly. Multiply by a inverse on both sides. That will get rid of the a on the right-hand side. And it will give me how many powers of a on the left-hand side? Give me jk minus 1 equals a times a inverse, identity. All right, so now we should be in a position to finish the argument. Because now we have a power of our generator, a, which equals the identity. But a is an element whose order is what? What's the order of the element a in this example? How many powers of a can make the identity for our a? Infinite. Right, well, we can't take an infinite number of powers, but you got the right idea. Our group has infinite order, and that means that the only power of a that's going to give me the identity, because I can take an infinite power, is what? The only power of a that's going to give me the identity is the 0th power. Right? Any other power of a, if it gave me the identity, it would mean that a has a finite order. And if a has finite order, this whole group has a finite order. Right? And we knew that wasn't the case. So, because my group, the order of my generator is infinite, that must mean that jk minus 1 is equal to 0. Only the 0th power of a can give me the identity. But if jk minus 1 is equal to 0, that means j times k is equal to 1. But j and k are both integers. And what are the only integers that can multiply together to give me 1? 1 in itself, or -1 in itself. Those are the only ways to multiply integers and get 1 as the answer. But why do we know that can't happen? Because we assumed that j was not equal to -1 and j was not equal to 1. Right? So neither j cannot be -1 and it cannot be 1, therefore we can't satisfy this equation. J times k equals 1. So that gives us a contradiction. Ugh. I would love to write this up as an actual... It would be a good exercise to do. Watch this video after class and then try to write up the formal proof version of it. But this resolves Casey's question, which is, can an infinite cyclic group have more than 2 generators? The answer is no. In fact, not only can it not have more than 2, it can't have less than 2 either. Right? It has to have exactly 2, because we know it's going to have 1 because it's a cyclic group, and we know its inverse is also going to be a generator. And then the last question is, why is the inverse of a definitely different from a? How do I know that this a and this a inverse are different elements? What if they weren't? What if a and a inverse were the same element? What would that tell you about a?
It's 1.
It's 1. 1 in what sense?
It's the number 1.
On my number line? Well, except on my number line where the operation is addition, the inverse of 1 is -1. So I want to know what happens if my generator is equal to itself. Or sorry, if my inverse of my generator is equal to itself.
Would that be a finite group?
Why?
because thinking along the lines of like the symmetries with shapes and stuff, T was the inverse of itself. So then if you were to have a cyclic group generated by T, you would have the identity T, the identity. So
Yes, exactly. Right. That's a great example. So you're thinking, what elements do we know that are their own inverses? Well, the reflection in a symmetry group, right, for a polygon. And if I only had, if that were the generator for my cyclic group, the only elements in that group would be the identity and then T. But then T squared would be equal to the identity again. T to the third would be equal to T. T to the fourth would be the identity again, right? And let's think about why that's the case in the abstract, right? If A is equal to A inverse, then what do I get when I multiply that equation on both sides by A? A squared equals the identity. And if A squared is equal to the identity, what's the order of the element A? It's 2, or it could be 1, right? But it's definitely a divisor of 2. But by our assumption, A was an element of infinite order, because we're an infinite cyclic group. So that guarantees for us that every infinite cyclic group has exactly 2 generators. Whatever generator is given to us by the definition, and then its inverse, which must be different from the original generator, because if it were not, then the order of that generator would be 2, not infinity. So what this really means, this is actually enough evidence to make the following conclusion. Every infinite cyclic group, so if G is infinite and cyclic, then what is G the same as? What group is G the same as, do you think? If our number line is our mental model, and we showed that every infinite cyclic group has exactly these 2 generators. I want to come back to Caitlin's observation for a second. Generator acts just like the number 1. In what group? What group does the number 1 generate? The group of integers, with addition being the operation. Every infinite cyclic group is just a sort of a lipstick on a pig masking of the integers. It is exactly just the number line. And in fact, we can find the number line right here in my list of elements, right? A to the first power, A to the second power, A to the third power, A to the minus 1, A to the minus 2. What power of A is the identity? A to the power 0. So where do I find the number line? I find it right here in the exponents. -2, -1, 0, 1, 2, 3, and so forth. And so what that does is it sets up a little dictionary where if I have any integer, k, over here in the additive group, z, then I just relate that element to a to the power k, where a is the generator for my group over on this side. And if I just correspond those 2 things, that shows me not just that these groups are the same, but how these groups are the same. Right? If you hand me an infinite cyclic group, I can hand you, for any element you hand me, I can hand you an integer, right? Just by taking the exponent out of that. And vice versa. If you give me an integer, I can give you an element in that cyclic group by just taking that power of the generator. Okay? So this kind of correspondence here between 2 groups, this is really a function from G into Z, or from Z into G. Right? And that function also respects the algebraic structure of those 2 groups in a way that we're going to talk about in Chapter 6. Because I've been beating around the bush about how to explicitly tell when 2 groups are the same. I've been using these words in scare quotes, same and different. So once we figure out what those kinds of functions are and how they operate, that's going to give us the power to actually definitively say when 2 groups are the same. And that's a particular kind of function called an isomorphism. Iso from same, morph from shape. So these 2 groups have the, quote, same shape. An isomorphism is a relationship between 2 groups that are, in fact, what I've been calling the same up until this point.